In this second video of nucleophilic addition, we're going to look at the addition of HCN across the double bond in an aldehyde and a ketone. And this is a way that you can convert aldehydes and ketones to hydroxynitriles. Now, hydroxynitriles have an OH group, that's our hydroxy part, and a nitrile, which is at the end of the chain. There's a C with a triple bond N. Now, we're going to do this by addition of HCN, although that is not the reagent. HCN comes from a combination of reagents, so we're going to be adding a H and a CN, but not from HCN. It comes from a combination of reagents which are KCN, so that's giving us the cyanide ion, KCN, and then we're going to follow that with a dilute acid. So a dilute acid could be something like hydrochloric acid or aqueous sulfuric acid. It's going to be a source of hydrogen ions. So KCN followed by a dilute acid. Now for our equation, we can just add the HCN formula, but in our mechanism we need to remember where they came from, so what our reagents were. So general equation for our aldehyde, remember that aldehyde has the structure R-CHO, CHO. We're going to add the HCN. And what we'll end up with is we're adding onto our aldehyde or ketone. So we remember that we still had a hydrogen already there. We've added a CN and across the double bond, and we've added a H to the O. So the CN has gone onto the carbon and the hydrogen has gone onto the oxygen of the double bond. This hydrogen at the top was already in the structure. If we look at that for ketones, we've got our structure with a C double bond O in the middle of it, and we add a H and a CN. Remember that we're going to add the CN to the carbon and the H to the oxygen. So we're adding a H and a CN across the double bond. This is going to increase, this is very important, this is going to increase the length of any carbon chain. We've added a carbon to the structure. Very important for organic chemistry. So I want you to pause the video and have a go at balancing these. If you find it difficult to write it in structural formula, just draw it out. And then see if you can name the organic product. You're going to have to name the organic product with the prefix hydroxy and the suffix nitrile. So these are our balanced equations, and hopefully we've got that far. The naming is a little bit trickier. If we look at the name, just to start off with, of our aldehydes and ketones, make sure we're happy with those, we've got a 1, 2, 3 carbon, and it's an aldehyde because it says CHO at the end, so we've got prop and al. Now at this side, the main functional group in a hydroxynitrile is the nitrile, so we have to start counting from the carbon that has the functional group, the nitrile. So we're going to count the longest carbon chain, and we've now got 4. So we're going to end the name butane nitrile. That's our stem of our main functional group. We notice though we haven't named this hydroxy group yet. So we're going to say that that is a 2 because it's on carbon number 2, 2-hydroxy butane nitrile. If we apply that same naming system to this example, we've got 1, 2, 3, 4, 5. Pentan, so we've got carbon-carbon single bonds, but with a ketone on number 3, pentan 3O. Now we have to name this structure of the hydroxynitrile starting at the nitrile because that's the primary functional group, 1, 2, and we can now go left or right because both carbon chains are the same length, 3, 4. So that's still butane nitrile. So it doesn't appear that it's increased in carbon chain length because it was pent and now it seems to be bute. Pent is 5, bute is 4. That hasn't got bigger, but it has got bigger in terms of number of carbons because we've got a substituent here and a substituent here that we need to name. They are both on carbon number 2, and one of them is a hydroxy group and one of them is an ethyl. We need to put those in alphabetical order, so we're going to say 2-ethyl, 2, remember that hyphens separate words from numbers, hydroxy butane nitrile. And if we count up now, ethyl means 2 and bute means 4, so in total we've got 6 carbons, so we have gone from 5 to 6. 2-ethyl 2-hydroxybutane nitrile. Hydroxynitriles are a favourite of the exam board, so make sure you feel confident naming hydroxynitriles. At the top of the next page we've got one more example. It's a little bit tricky because we've got this bracket at the end, so it might be worth sketching it out. So I'm going to do this one live, I'm not going to pause the video. So I'm going to draw that first CH3 that comes in a bracket, and the second CH3 is also attached to the same cavity. I'm just going to draw that out like that, and then put that hydrogen sticking up at the top there. Then I've got a C with 2 H's, and then I've got my, what was my aldehyde or ketone group, where I'm going to do my addition reaction. So I had the H, the O got the H from HCN, and the C got the CN. So there's my structure of my product. I start counting. 1, 2, from the nitrile, remember, 3, 4, 5. So this is going to be called pentanenitrile. It's got a hydroxy on number 2 and a methyl on number 4. Remember, we put those in alphabetical order, so this time the hydroxy comes first. And we get 2-hydroxy 4-methyl pentanenitrile. If we wanted to go back and name the aldehyde, it did actually have 4 in a row. It was called 3-methyl butanal. So it had 5 carbons in total, a but 4 and a meth 1, 5, and now we have got a meth and a pent, we've gone to 6. So how does this mechanism happen? The name of the mechanism for aldehydes and ketones is nucleophilic addition, and our reagent is KCN followed by dilute acid. Exam board like you to be able to say that. Remember that our dilute acid contains hydrogen ions, but out of this, what's our nucleophile? So you need to think about what is a nucleophile. Nucleophile is an electron pair donor. Remember, no K in mechanism, no metal in mechanism. So we can look at our cyanide ion just like in our halogenoalkanes, and remembering that the lone pair on the C is the one that causes the minus charge. So it's going to be a CN minus. Let's write out ethanol. And draw out our nucleophile. So although we say KCN, we don't want the metal, we only want the nucleophile. So we're going to have our CN minus. I'm going to draw a curly arrow from our lone pair to our carbon. Remember, it goes for that carbon because that carbon is delta plus, because oxygen is more electronegative. And we're going to break the pi bond, the double bond, and put the electrons onto the oxygen. So in that first step, we've added the CN to our structure. So far we've added the CN. Remember that this connectivity must go from the C to the C and not to the N. And we've broken the double bond and given oxygen a pair of electrons. Now what happens is we're adding the dilute acid, which is a source of H+, and off we go to pick it up. So remember, from this we're using the CN and just the H, we're not using the K or the Cl. And we have added the H to the oxygen and the CN to the carbon. And if we were to name that structure, we'd start from the nitrile, carbon, and we've got propane nitrile with a hydroxy group on number 2. So 2-hydroxy propane nitrile. So pause the video and see if you can do that mechanism, but this time with propanone instead of ethanol. So if I had a go at that, you should have got something like this. So the cyanide ion with its negative charge is a nucleophile. It attacks the delta positive carbon, creates a new carbon-carbon bond. The pi bond in the carbon-oxygen double bond breaks to make an O with a minus charge. The lone pair of electrons then goes to pick up that H+ ion from the dilute acid to create our hydroxynitrile. So scroll down and have a go at pentan 2-one and see if you can do that again. You should have got something looking along the lines of this. Hopefully you've managed to get all your curly arrows neatly and accurately drawn. The exam board are really looking for those. Do they start from a lone pair or from a shared pair, a covalent bond? And do they go where you want them to go? So make sure that they go in the direction of the flow of electrons. If you really want to challenge yourself, what you could attempt to do now is draw that mechanism but using skeletal formula. Now when we start the nitrile mechanism, this hydroxynitrile mechanism, the cyanide ion isn't organic and therefore you will just be able to draw that out as a CN, but at the end it's part of the organic structure and carbons are not shown. So see if you could have a go at doing that in skeletal formula. There you go, that is a bit of an extension activity there for you, but if you've had a go at that and you've managed to draw that, well done.